Hey friends, welcome. And today I'm going to discuss about a very important problem. The problem is important because the stereochemistry involved in this particular case is very complicated, and you have to understand it very well. Otherwise, you will be like you will not get what is going on here. So the options are given like this, right? So now this is the molecule. It is a conjugated enone, and first it is reacted with phenyl magnesium bromide in presence of copper salt. So it will do conjugate addition, that is 1 for addition. It will attack here, and then work up with H3O plus. Then when you get product A, this product A is now treated with sodium ethoxide and bromine. It will give product B. So first of all, I should write it in the cyclohexane half chair form because it is cyclohexenone system and it will be in the half chair form. So this will be your half chair, and here you have the ketone. Now you know the axial attack will occur because that will go through the chair like transition state. So your phenyl will attack here, and you will get this O minus, and here you have phenyl. Okay, now you can write the same thing. You can write like this. These two are same. So then when you work up with acid, you are giving a proton source. So the work, when you do work up, this is actually the protonation occurs in this step is kinetic protonation, and that will be that will give the kinetically controlled product. And you know that in any this type of system where you have two possibility, one is axial attack and one is equatorial attack, the kinetically favored attack is axial attack, right? So from your kinetic attack you will get this product. So here you have hydrogen, and here you have methyl phenyl group. So this is your product A. So in your product A, what is the configuration? The configuration is such that the both groups are in the same direction. COMe and your phenyl, they are Cs. Okay, they are Cs. So this is because of this axial attack. And why axial attack is actually preferred in kinetically controlled reaction? Because in this case the reaction is occurring from the HOMO of this enolate, and although it is a pi bond, but in the earlier transition state here a sp3 type hybrid orbital is generated, and that has higher coefficient on the axial phase like this, because when it undergoes alkylation, the more bulky group, the proton is protostatically very small compared to this COMe group, and that's why when it undergoes protonation in the earlier transition state, it slightly bends towards this equatorial position like this. Okay, although there is a double bond, you can show it like this. So actually it is O minus. Okay, so from ideal planar configuration, it will slightly bend toward the equatorial side, and that makes this HOMO more exposed compared to the equatorial phase, and that's why protonation will occur from here. But this is, note that this is your kinetically controlled product, because these two groups, two bulky groups, are in the same side, that is not thermodynamically more stable. So from step 1 you get kinetically more stable product, kinetically more favorable product, this one. Now this particular molecule can be in two configurations. So this is your actually this you get, and this can exist either like this or it can be flipped. So when it flips, you will get what you will get, you will get this one. Okay, so these two configuration you can get. And in this case, in both of this case, if you add a base like sodium ethoxide, so what will happen, it can take a acidic proton, and there are two. So I am talking about the second step, and there are two types of acidic proton. Either this is acidic proton and this is also acidic proton, because both are adjacent to the carbonyl group. So in this case also, this is one acidic proton and this is one acidic proton. Okay, so from this particular isomer, if you take up the acidic proton, and you will be getting this. So if you take this acidic proton, you will be getting, so you are abstracting this proton and you are getting this one, your phenyl group is here. Okay, and if you take the same acidic proton from here, you will be getting this O minus methyl, and this is your phenyl. So this particular isomer you can write like this also. So this thing you can write like this, they are same. O minus methyl, and here you have phenyl. Now note that this particular center, this particular portion is similar to this. So let's say you have a methyl group here and you have phenyl group here. So they are in these two groups are in the same plane and they are C's. So the angle between, so this group and this group, the angle between these two groups are near 4 degree. So they are actually eclipsed, and this is called 1,2 allylic strain. Actually 1,3 allylic strain. And due to this 1,3 allylic strain, this enolate formation is not favorable. So this enolate formation will not occur. Instead, this proton will go, because it will give you this enolate pH, and then you have this CO, sorry, this enolate will occur. So from this particular isomer, this enolate formation will be occurred and not this. And in this, from this also this enolate can be formed, because in this case also this hydrogen is more accessible. Now what about this one? So this can form. Now you have bromine molecules, Br2 molecules in your medium, because in the second step they give sodium ethoxide and Br2. But in this case, in the question is not mentioned, but it may be that the bromine molecules are present in one equivalent. Okay, and in your total assembly, this particular enolate will be more populated than this, because all the way this hydrogen is less accessible, right? And they are although the phenyl group is in this case there is no allylic strain is there, this will be very less, the amount of this will be very less, so more, so you will get more this enolate will be more in your medium. And when you brominate this, so this enolate will attack here, and you brominate this particular isomer to give you this bromine. Okay, Now, and in this case, instead of undergoing bromination, they can again they can again undergo protonation, because sodium ethoxide, when take proton, it will form ethanol, and it can take proton from ethanol like this. So in this case, the protonation can be either occur from your axial side or from equatorial side, right? So this protonation can occur from either axial side or equatorial side. And if you protonate from your side, then you will get the same thing as you have previously, like this. But if attack occurs from equatorial side, you will get this one, pH, which can flip to give you this pH. Sorry, so I am not, so actually when it flips it will look like this, and you have your COMe group here and your phenol. So now both are equatorial, and this it will be major means almost all will be this, not this diaxial form. Population of this diaxial form will be less than 1%, and it will be more than 99%. So almost all are in this configuration, right? And in this case also, this product, initially this will form, but again you have sodium ethox. So now this product which you get, it can flip. So it can flip to give you this. What happens, your phenyl will be now axial, and your this group will be equatorial. Okay, now your bromine is used in one equivalent, although it is not mentioned in the question. I think it should be one equivalent, otherwise you cannot explain the product. So your bromine is consumed by your enolate, but sodium ethoxide is left there, and it can again take this proton. All possibilities are there, it can take proton, this proton also, but that doesn't matter. If it takes this proton, you will be getting this intermediate Br and phenyl. Now again, formation of this intermediate is favored, because in this case, due to the presence of this phenyl group in axial position, there is no allylic 1,3 strain, and then when it comes back, it can take proton from equatorial position or axial position. But if it takes proton from equatorial position, you will get this uh, CO here, and this, which can be flipped to give you this product, phenyl equatorial, and your this group also equatorial. Okay, so see, this product is much more stable. This product is very much stable, and it is thermodynamically controlled product, because both groups are actually equatorial. So this is thermodynamically controlled product. And so in basic medium, the protonation is actually thermodynamically controlled, because in this case the protonation is slower, because the protonation is occurring from these ethanol molecules. In the previous case, when you do workup, you give H3O plus, that is acid, direct acid you are giving, so that step is kinetically controlled. But in this case, the protonation is thermodynamically controlled, and that's why the thermodynamically more stable product is forming. So what is conclusion is that in your product, the product you will get this one. So if your phenyl group is up, then your this group will be down, because they are trans. In your final product B, they are trans. So how this cis trans isomerization is taking place now? I in some place I wrote another intermediate which doesn't undergo bromination but only protonation deprotonation, and that was simply your this one, right? So it can again undergo bromination by forming this enolate. And then this bromine, so it will undergo this bromination to form this enolate. Okay, so either way this trans configuration is your product. Now this explanation may seem slight uncomfortable uh, because although the enolate is forming, the bromination is not occurring here, but uh, you may find you may search for any book, but you will not get any other explanation instead of this. So either the question is wrong, so the main point is that when you have, so in this question the main concept is that if you have a system where you have two groups like this and you are forming enolate, you are having two options, either this proton or this proton. Okay, now uh, although both, this proton is obviously more accessible because it is sterically free, but this proton is also accessible. There is a difference but not that much that only this will form. But if the fact is that only enolate will form from this side, that is you will always get this enolate and you will never get this one where you have this O minus and phenyl and this. So you will never get this because of this 1,3 diallyl interact 1,3 diallyl interaction. This is allyl system. So due to this 1,3 interaction, this enolate you will never get, you will always get this enolate. So this is the main concept of this reaction. Now how this stereochemistry is inverted in the product, because in the product A both of the groups are cis, but in the product B you are getting trans product. So I think that in the assembly of the molecule of A, there may be some point when the phenyl is equatorial, and in that case you can get this. Okay, or after consumption of all bromine, then this type of thing can occur, because this is not favorable. This is although this is allylic 1,3 strain free, but you are placing this phenylic axial, so this is also not that much favorable. But you have to explain the product, so in this way it can be explained. So the take home message from this uh, problem is that if you have this type of system where you can get allylic 1,3 strain, you will always analyze this side and not this side. So this problem is very important, and if I get any further explanation for this, I will let you know, but for that moment I don't have other explanation. If you know it, then you can let me know in the comment section. So thank you for watching, and please subscribe my channel.